All right, so today what we're going to do is wrap up Monte Carlo simulation, and we're going to start the next chapter, which is finite difference methods. So before we do anything else, I just want to mention that I think we're pretty much done analyzing the code for this Monte Carlo simulation of a European call option. Let me just open up the code for a second. Yeah, so you can see there's a lot of documentation, but the code is itself is pretty straightforward. I just want to mention that down here at the bottom, all this part down here, this very mysterious this part here is just a way of calculating a standard deviation and a standard error for the results that we're getting on all these paths, which makes it possible to construct a confidence interval. It looks very bizarre, but that's all that it is. The code itself is really right here. You know, we have paths, m paths, and on each of these m paths we have n steps, which we can set to anything we want. But it turns out that the number of steps on each path doesn't really affect the convergence speed, or really the accuracy for that matter. It doesn't seem to change our results very much if we have more steps on each path. This is the one that really determines the final results. The number of paths, if we keep increasing the number of paths, the standard deviation keeps shrinking, and therefore the confidence interval gets tighter, and so we get closer and closer to our target, which is to replicate the Black-Scholes price. So in the code, you can see that we have a loop for the m, which is the paths. Within here, we have a loop for n, which is the number of time steps. And on each step, we need a new random number, which is epsilon. And as we've already seen, this is indirectly at least taken from the standard normal distribution by first taking a number from the standard uniform distribution and then plugging it into the inverse of the standard normal distribution. And also we're modeling the log rather than the actual stock price here, because it can speed things up a bit. And of course with Monte Carlo, speed is of the essence because it's a very time consuming process. But of course that means at the end we have to take whatever the final result is. The actual price of the stock is E raised to that log stock price. And then the option price is based on the stock price. And so ultimately what we're doing is we're creating a large number of possible payoffs for this option. And then the average of those payoffs discounted back to the present is our estimated option price. Okay, so now what we're going to do next is look at an interesting area, which is something called variance reduction techniques. Now, it turns out that because Monte Carlo simulation is just so terribly time consuming, researchers have looked for techniques that might be able to speed things up a bit. And these are all collectively known as variance reduction techniques. Now, we're only going to look at one or two of them because they're very straightforward. There's many others. There's all kinds of things we could do, but I think you'll find this one kind of interesting because basically what we're doing is this. You might remember from statistics that when you have a sampling distribution, the standard error is inversely proportional to the number of the sample size that we're using. And so we're going to use a similar concept here, which means what we're basically doing, we show the graph before you go any further, is instead of taking individual paths, oh, I thought there was a graph here. Sorry, let me go open up a document so I can show you what we're about to do. Let's see. So this approach we're about to take is called antithetic variables. Oops, I think I spelled it wrong. Yes, I did. Oh my God. Antithetic variables. Okay, so with this approach to Monte Carlo simulation, instead of simulating a large number of paths, Instead, a large number, well, not a large, somewhat smaller number of pairs of paths. Well, I guess there's no point in putting quotes here. Pairs of paths are simulated, and the averages these paths are recorded. So, in other words, let me just quickly show you what this means. So you've got here is whatever variable we're simulating. Let's say it's a stock price, and we want to price an option on this stock. Here's the maturity date of the option. And with traditional Monte Carlo, if let's say this is our strike price, would have a payoff, of course, equal to, because by the way, this is assumed to be a European call option. The payoff equals max ST minus zero, which you can see in this case is positive. And then we would do that a very large number of times. And then for each one of these, we calculate the payoff on the maturity date, and then we average those out, and then we calculate the price of the option as the present value of that average payoff to the option at the maturity date. So, and I think I remember I drew a little graph here where it after a while it starts to look very cluttered. So in other words, what you're doing here is creating a probability distribution for ST. Okay. And this now, by the way, because of the assumptions of the Black-Scholes model, that probability distribution is log normal. So it should look something like this. And the center, let's say it's here, is the number that we're looking for. We're averaging them out. And that number, so the option price is simply the present value of, actually, this becomes capital T. So that's what we're doing with the traditional Monte Carlo approach. But with this new approach, we're doing something a little different. And you may at first think that this is not such a smart thing to do, but you'll see pretty quickly that actually it's the other way around. For each path that we generate with this antithetic approach, to do is this. All right, so there's our path. We're basically going to take a mirror image of that. Okay, well, that's not a perfect diagram, but the idea here is that top, above, and below should be identical to each other. And so what you have here is, we'll call this ST1 and ST2. And so the payoff is based on the average of those two. And then again, just like with regular Monte Carlo simulation, you do this many, many times. You have a probability distribution. You discount it back to the present. So each price, though, is taken from a pair of paths rather than a single path, which makes you think, well, isn't this twice as much work? You would think so, but the reality is, because these are averages, the standard error is being reduced proportionately to radical 2. And so you end up with the possibility of getting the same level of accuracy with fewer paths. If you, um, let's say, for example, before we needed 1,000 paths to get to a certain degree of accuracy. Now we might be able to get away with 400 pairs of paths to reach that same level of accuracy. So the details are in the slides, but it has to do with the fact that an average like this has a smaller standard deviation than the actual paths themselves. So this, and now, by the way, this turns out to be very simple to implement in the computer. And so that's one of the reasons why it's so popular. So what you're actually doing here is this. Well, this is, of course, this part hasn't changed. But what's different is that when you're generating the path, the original path, let's say, is the one on top. You notice how epsilon is here. Epsilon is plugged into this model, okay, which we've seen before. The others are constants. We presumably know those constants. And then epsilon is what's being simulated. But then what we have to do is go back to create the second path, is store the epsilons. And then what we have to do is replace the positive epsilons with negative epsilons, the same value, but negative. And then the positive ones, sorry, the negative ones become positive. Okay, so what you're doing is you're changing the signs of the epsilons and recalculating the stock price. And so you end up with two paths that will look similar to this. Okay, in other words, they will be mirror images of each other. And at the end, we're capturing the average of the two, and that will give us a single payoff. And then we average out all those payoffs, we discount them back to the present, and we have a price. But we can show that this will reduce the processing time by up to 25%. So, um, here's what we're going to have to do. At some point, we have to have assignments. All right. So we've been kind of having too much fun to have assignments up to this point. So you do have a copy of this European options code. And I'm going to give you ask you to go ahead and take this code and update it to run these mirror image paths. And so in other words, what you would have to do is go into the code and here you're basically going to create two paths at once. Okay. In other words, while this one is in progress, you're going to also extend the second path. So you're basically doing two paths at the same time. And when the loop is done, when you get to the end of the path, just average them out. And that becomes one observation. We need to do this m times, and we discount the average, and we'll be done. So it's pretty simple. So I'll give you a chance to work on it and then see what you can do. If you get stuck, I'll give you some help though. But it comes down to what's happening here. Okay, so remember, the whole idea here is that you're replacing positive epsilons with negatives and vice versa. So you have two paths, and when you're done with that loop, you should have an average instead of a single path. So that will be your first real assignment, okay? So, like I said, it shouldn't be too difficult, but if you're not sure what to do, we'll go over it. Now, when that's done, by the way, a lot of the assignments are going to come from this chapter because the code is pretty straightforward, but what I'm going to have you do is try other more complicated options using Monte Carlo simulation. And you'll see that it really isn't that difficult. That's one of the reasons why this is so popular. It's just a question of knowing what to do to the paths to adjust them for the different types of options. So in other words, we'll be doing some very interesting exotic options with our Monte Carlo simulation. Okay, so very little will need to be changed to this code to get to the antithetic variables approach. And then we can run it side by side with this model and see what a difference it makes to the standard deviation and the standard error. And you'll see it does a pretty good job of reducing the standard error by a surprisingly large amount. Well, anyway, so that's that. So now we're ready to go on to this finite difference methods, which in a way is just it's kind of a more general approach to what we've already been doing. There's actually three ways of going about this. And by the way, these are meant to replicate. Think of these as kind of a discrete time version of differential equations. And you'll see that the explicit finite difference method, which is the one that we'll be looking at here, is essentially a more general version of the trinomial tree model, which means that it's easy to keep track of all this information. So we're going to look at the evolution of an asset's price over time in terms of a difference equation. And so difference equations are pretty straightforward. I mean, all you're really doing here is this. Like, here's an example of what might be a difference equation. Something that's simple. It just means that whatever A is today, it has a constant term. It has a slope, and the variable here, at minus 1, is simply the previous value of this variable. Okay, so this would be a simple example of a difference equation, and specifically, this is a first difference or first order difference equation. And then you can visualize that there could also be a second order difference equation where we go back 2 time steps. So, well, you'll see how it works when we get involved with this, but in just the most general possible terms, you could think of these as difference equations where the value of the variable at any particular time is a function of its own past values. Oh, okay, we can put this one away. So, now, the first thing that's going to be different here, and you can see why this will be very easy to program, because you can see that we're going to create a grid as opposed to a lattice. Those other methods we looked at were lattice methods. Binomial and trinomial trees were considered to be lattice methods or tree methods. Here, we're going to fill in an entire grid of values, so you can easily reproduce this as a matrix. And normally what happens is we have the asset price on the vertical axis and time across the horizontal axis. And that makes sense because it means that S is a function of T. So, of course, there are some important differences. We have an asset step as well as a time step. So in other words, you can think of this as delta S, which is going to be a constant throughout the entire grid. And then this would be delta T. And you'll see how we determine those in a minute. The way the indices work is that asset, in other words, moving up and down is indexed with J. Hold on 1 second. So yes. I equals time. Okay, we're going to need that when we write the code because you'll have I and J. I will be the passage of time, meaning as we move across the horizontal axis, J will be the level of the asset, meaning how far up and down have we moved. Capital M will represent the upper and lower boundaries of our grid on the vertical axis. Okay, so in other words, you have to visualize it. We start here, let's say. this would be defined as j equals 0. And then you'd have, this would be j equals 1, j equals 2, j equals 3 up here. This would be then, actually, let me fix this real fast. They're kind of in the way here. Let me move these. And then here you'll have j equals -1, -2, -3. So here you would define capital M as 3 because that limits the number of upward and downward steps to 3. So when you see the code, you'll see that capital M represents the maximum number of upward or downward movements. S0 would be where we start. And then S1 would be S0 plus delta S. Okay. And in general, S, the more general expression would be Sj could be written as S0 plus J times delta S. Okay, and it just shows me that J is telling me how far up I'm going. Each time I go up by delta S. So I'm adding that to the initial stock price. Delta T is the size of a single time step. And that would be the total time involved. We're going to use the capital letter T to be the total time until the end of the grid. And then capital N is N is the number of time steps. Okay. Now, of course, time can't go backwards. So M will go from 0, N rather, will go from 0 up to the maximum number of time steps. So the J is the only one that can be negative. So the time at any given point is I delta T. Okay, so capital N is the number of time steps until we reach the maturity date here. And that in turn implies that delta T is equal to capital T over N. So it's easy to keep track of this information because we're just going to let it be F or S if it's the stock price tree, Fi comma J. I is the row, or actually I is the time. I is not actually the row. I is the time that has elapsed. J is the level. So you could actually, that means that these are kind of backwards from normal matrix notation, where normally it's row column. Here it's the other way around, column row. Okay. Now, by the way, going on behind the scenes of the Black-Scholes model, they derived this differential equation to explain the evolution over time of the asset price that we are underlying the option. Okay, so if it's a stock, for example, this is the differential equation that they're using to show how it changes over time. So, for example, this time, we've got a first and second order partial derivative for the stock price. So in terms of deltas, not deltas, in terms of the Greeks, you can think of this as theta. Remember this from the last class, we introduced the Greeks. Theta is the sensitivity of the option price to time. This would be our delta, and this would be our gamma. Let's see, we have, and R minus Q is the drift of the value of the asset in a risk neutral world. And of course, you notice how we have minus RF over here, because we're assuming that in this framework they developed, the return to all assets equals the risk-free rate. Now, the reason why this matters is because what we're actually going to do here is we're going to model the stock price by taking these partial derivatives and turning them into what are called difference equations. Okay, so delta F over delta T can be thought of as the change in the F. And by the way, if you notice these indexes or indices, a change in I means that time is evolving. So according across the horizontal time axis, if we start with I equals 0, which is today, I equals 1 would mean next period. And so if you notice, the index changes for time, but not for the level. So that means we're staying across the same path. And say here we have F ij, and this would be F I plus 1j. So the difference between these two with respect to this size of the time step is this partial F partial T, or in other words, the theta of this option. You might recall that the theta is actually a negative number. Just a quick refresher. Theta means is a measure of how much time value an option loses as time evolves. So just another quick reminder, when you look at a graph of, let's say, a call option, at any time prior to the maturity date, you're going to find the market price is greater than the payoff. Let's say this is 3 months before the maturity date of this option. So if, let's say, the stock price is here. Oh, whoops, sorry. I did the wrong thing here. This should be S and this should be dollars. So right here at this point, I'll call it S star. This is the payoff to the option. The market price is up here. The spread between these two is the time value of the option, which means that the reason why there's time value is because depending on how long it is until the option matures, there's a pretty decent chance that the option will continue to gain in value, and that's what you're paying for here. As time elapses, though, the market price gets closer and closer. Say it's now 1 month from the maturity date. And you can see that if the stock price hasn't changed, the price is shrinking because not the payoff, it's not the payoff that's changing, it's the time value that's shrinking. And on the actual maturity date, the price line will coincide with the payoff. Okay, they'll be identical to each other on the maturity date. And at that time, the time value of the option is zero. So the theta is telling me how quickly this is happening. All right, so um, theta captures how much time value is lost as single trading day or as a result of a passage of a single trading day, although it is often annualized. Because these numbers would be quite small over a single trading day, but sometimes they're quoted on an annual basis. Okay, so that's what theta means. Let's see where were we? Now, this is how we're going to calculate on this grid. Okay, so again, you can see I is the time variable. As we move across from left to right, we want to know how much the option price changes as a result of the change of a single time step. Oh, here we go. This is a good example. You can see here what's actually happened. As we go from left to right, as time evolves, the option here that hasn't actually, the stock price hasn't changed, but what has happened is that you have a different option value. And so the change will reflect the loss of time value. Now, by the way, they'll make the point here that there's more than one way of doing this. If you notice here, we're implicitly assuming that we're going from left to right. That's known as a forward difference. Going the other way is, as you can probably guess, known as a backward difference. Now, you're probably wondering, well, which one should we use? It depends on what we're trying to do. Sometimes one approach works better than the other. Sometimes it doesn't make any real difference. But you can see here that what's changed is that instead of I plus 1 and I, so the backward is this one. So like I would be today. Okay, whatever time is today is I. Here you're looking at yesterday, the other one you're looking forward into the next one, the next time step. Now the delta, as you can see, instead of the I's changing, it's the J's that are changing. Time is not changing, but the level of the stock is changing. So that would be this case where you're going up the grid. Okay, so in other words, now I is held constant because that's the same time step, but J is being allowed to go up. So this will let us capture how much the option price changes when the underlying stock changes. And once again, this is a forward difference. The backward difference would be, oh, okay, it would be down here. Means you'd be going down, basically. Let's say that I have Fi J minus 1. Okay. Now, I remember before I mentioned that with difference equations, finite difference equations, that is, sometimes we see first order, sometimes we have second order. The gamma requires a second order difference equation, because you notice what's happening here, going from j plus 1 to j minus 1. We're going two steps. And that's because what you're actually doing here is this. Oops. This one should be j minus 1. And so when you cancel out all these terms, oh, actually, no, you know what? That's not what, okay. I have to go look up the derivation again. I just realized I'm goofing it up here. I'll go look it up separately, but it's a difference of differences. That's the bottom line. Okay, and that's how it gets to this form. And if you notice in the denominator, we have 2 because there's 2 time steps involved. And this is sometimes called the central difference because in effect, you're averaging out a forward and a backward difference. Oh, maybe that's where I went wrong over here. Averaging these two out. Yes, that's right. And that's where the 2 would come from. These drop out. There we go. That's what I needed. This minus this is divided by 2. And then the delta S shows me the times, the level, the change in the level. Now, the central differences actually can be a little bit more time consuming, but they can also help improve the convergence of what we're doing to the true price of an option. So in other words, numerical methods, which is what we're using here, are designed to approximate the solutions to functions that cannot be solved directly. So how do we decide whether they're working correctly or not? Now, in statistics, interestingly enough, this is what's being done to solve the t distribution. It doesn't have a closed form solution that we can use like the normal. And so the computer has to basically search for the answer that is as close as possible to what we're looking for. So the 2 ways we can judge whether a numerical method is actually working correctly is to look at its convergence and stability. The convergence means that we're getting closer and closer to the true solution as the step size equals 0. Like remember with the binomial tree, we only have 2 time steps. The chances are pretty good that we're not going to have the correct Black-Scholes price. But if we have 2 million, no, maybe not 2 million, but 2,000 steps, then we're going to get awfully, awfully close to the true Black-Scholes price. And that means that the binomial option pricing model is convergent. Now, if the now, by the way, they're making the case here that because we're trying to essentially reproduce a continuous process with a discrete time model, there's going to be, of course, errors involved. But what we're hoping for is that the size of the errors will continue to shrink. And that means both positive and negative errors as we get closer, the time step closer to 0. So let me just see if I can draw some pictures here. So convergent would be something like this. Let's say we're trying to simulate the Black-Scholes price with let's say the binomial option pricing model. And so here's the number of time steps. And here we have the Black-Scholes price. So what'll typically happen is you may start fairly far away from the true Black-Scholes price, but eventually it'll get very, very close to the true Black-Scholes price. That would mean convergence. Stability means that as we shrink up the time step between the step between time, what will happen here is that as we get further to the right, you notice how in the beginning the errors are quite large, positive and negative, but then as time elapses or the number of time steps increases, we're getting smaller and smaller differences from the Black-Scholes model. And that would mean that this is stable. Actually, I'll tell you, let me show you what unstable would look like. Some nonsense like that. In other words, as we get closer, the number as n is increasing. There's no the error can go up and it can go down. Whereas with stable, as n increases, on average, this error is getting smaller and smaller. And that's what we mean by stable or stability. Whereas convergence simply means as we increase n, we're getting closer and closer to the Black-Scholes, however we get there. Okay, so they're two different things, but we want to see both of these in a numerical method for us to have any confidence in it. And luckily we can prove, and it's been proven in the literature that the Black-Scholes, the binomial option pricing model, trinomial option pricing model are both stable and convergent. And so is this method we're looking at now, which is the finite difference methods. If not, we'd have to try something else. Okay, you can't have a case where as you increase the number of steps, that the model gets worse. That just doesn't work. Oh, here we go. The second difference. This is for the gamma. All right, and that's the final result for gamma. This is the difference of differences. That's why it looks like this. And you notice in the denominator, it's delta S squared. Now, what's going to happen is we're going to take this differential equation, which is actually it's actually a partial differential equation, and we're going to make some changes. We want to model the log like we did with the Monte Carlo, rather than the asset price itself. So we have to make a couple of changes, which are we're going to replace s with or x rather with log s, and v, or which is actually the Greek letter nu, as r minus q minus 1/2 sigma squared, which means that we end up with this model for the log of the stock price. And now this is a little bit easier to reproduce on the grid. And so what happens here is that we go into the grid, like, well, here's what I mean. We fill it in, and in order to figure out from, let's say this is the maturity date of the option, these are the three values of the option. We're going to calculate the weighted average of these three results and discount them back to the present to come up with this number. And now, because there's three branches, like with a trinomial tree, if you recall, we have PU, PM, and PD instead of just P and 1 minus P. So that means we must have. So yeah, just like with the binomial option pricing model, except that there's three branches. And so you can see this does look a lot like the trinomial tree, doesn't it? The trinomial option pricing model. It is very similar in a lot of ways, except that it's taking place within a grid instead of an actual lattice. So now, of course, because there's more than two branches, we need a new set of definitions for PU, PM, and PD. Okay, so those are here. Now, these are in terms of not the stock prices themselves, but the logs. Okay, so remember, X is meant to represent the log of the stock price. So you can see there's no S's in here. We have X. And so there's three of them. And I think I'm not sure if it's worth a while to try to derive these probabilities. Probably not. I mean, it's getting a little late in the course, so we may as well just carry on and learn how to do this on VBA. But it would have been a moments method approach, just like we had in the trinomial tree. Now, here's something you don't see in the other methods. We need to have some sense of how big the grid needs to be, not just how much time we want, how large the time step should be, but how large or how small can the stock price realistically get? So in other words, it's this capital M that we're thinking about now. Let's go back to that original graph. Okay, so here, I guess I didn't write it down, but M is 3, because that is how many steps up we're allowed to go and how many down. So what they will have us do is say, listen, the top of this grid is where the call option is so deeply in the money that it's virtually guaranteed to be exercised. The bottom is the other extreme. It's so deeply out of the money that it's virtually guaranteed not to be exercised. So what we often see is that we'll have on the top, we'll simply assign the payoff to the option on the top row and 0 to the bottom row, because we think of those as the extreme outcomes. All right, let's see. So we think of these are called boundary conditions. So whatever is the highest value we believe the stock price can reach over this time frame, we'll call this S max, which equals the maximum M times delta S. In other words, M upward movements. Then of course we'll have S min, which is 0, of course. Um, so that means that when we reach, remember, this is time, and this is the level. If we replace J with M, that indicates we're on the top. And then here, it's the other way around. Okay, so in other words, within a given time step, this is the top of the grid. This is the bottom. So that establishes the limits on how high or low the option price can go. And then we have a boundary condition to make sure that it doesn't go over that. On the top, you can see that we have the maximum stock price. Now here, if you notice, well, this is certainly the strike price. Discount factor has R here, but if you notice, it's I delta T instead of T, because where we are depends on how many time steps there have been since the start of the process. So that's the interesting part. With Black-Scholes, remember, we had uh, so it looked like this, the discounted value of the strike price. But here, to indicate this depends on what time we're at right now on the grid. Where are we located across the horizontal axis? But basically, it's the same thing as the payoff to an option that is finished in the money. So if we reach the top of the grid, the payoff would be the stock price. And then here we have X, which is, that's actually, earlier on, we were looking at some boundary conditions. And this is one of those boundary conditions. But anyway, the bottom is easy, it's just zero. Now, if we are pricing a put, of course, these are reversed. Reaching the top means the option is worthless, it's out of the money. And if we reach the bottom, then we have the payoff. Now, the other two alternative versions here are called implicit finite difference method, which we'll kind of steer away from because it is, it has its advantages, but it's terribly complicated compared to the explicit. And it doesn't have that same nice connection with the trinomial model. And then this Crank-Nicholson method is basically an average of the two. And again, it's very sophisticated, it's very stable, it converges quickly, but it's horribly complicated. So what we need to do now is at least open up the code and take a quick look at it to see where we're going with this. So of course, we'll start with the American call. Now, oh, I just forgot this one. Oh, I forgot to tell it. Now, what I did here was I was able to put together not only the code, but this is the grid that this model produces. And so those are the stock prices on the entire grid. This over here is the resulting call price. But I think it's helpful to have access to this grid where we start at time zero. And you can see the maximum number of time steps is 3. This would be J equals 0. And these would be -1. Okay. And so that is the result. Now, as you can see, right here, we have today's option price. Down here, the option is out of the money. So in other words, unlike with the binomial option pricing model, here the entire grid is filled in. So we can easily store this as a matrix. We just have to be a little bit careful about the indexing because again, you notice that the I is actually a column and J is a row. So we'll see that when we look at the code. Then we have capital M, which is the maximum number of upward or downward movements. And then we have some other constants that we're used to seeing. For example, dt is the time step. Nu is the drift term. Dx is the size of an upward movement. E to the dx is just what it sounds like, e raised to the dx power. And then we have the three probabilities. So if you look at the code, let's see, how much code do we have here? Well, not much. Because of the way it's been set up. Actually, it's a little bit messier. I shouldn't say that. Um, but it's not. Now, by the way, this part down here is just to create that little grid. You don't need to do this, but it's kind of fun to have a grid. So you can see all of the numbers. So, you know what I'll tell you, next time we'll go through and look at the code here. I think we'll have to stop because it's already close to an hour. And next time we can pick it up right here. And then in the meantime, don't forget about that assignment. You want to take the European option, sorry, the Monte Carlo code for a European call option and turn it into the antithetic variables model, which means you're creating paths, mirror images of your paths, and only storing the averages of those paths when you calculate the price of the option. Okay. So, all right. Anyway, so I'll just stop it right here, and then I'll see you next time.